Welcome to this problem walkthrough. In today's session, we'll be tackling the problem titled Missing Number in Arithmetic Progression. This problem challenges us to identify the missing number in a sequence that follows an arithmetic progression. We'll explore the brute force approach to better understand the solution. Let's dive in. In this problem, we are working with an arithmetic progression, which is a sequence of numbers where the difference between any two consecutive elements remains constant. For example, the sequence 1, 3, 5, 7, 9 has a common difference of 2. Now, what makes this problem interesting is that you're given an array that represents an arithmetic progression, but one element is missing. Your task is to find and return this missing number. Let's look at an example. If the input array is 5, 7, 11, 13, the output should be 9. This is because the difference between consecutive numbers is 2, and 9 is the missing value that completes the sequence. Here's why the output is 9 in the first example. The array 5, 7, underscore, 11, 13 has a gap between 7 and 11. The common difference of 2 tells us that the missing number must be 9 to maintain the progression. Now consider another example. If the input is 15, 13, 12, the output is 14. This time, the array 15, underscore, 13, 12 has a missing number between 15 and 13. The common difference here is -1, so the missing number is 14. Finally, in the third example, the input 1, 3, 7 leads to the output 5. The missing number in the sequence 1, 3, underscore, 7 is 5, as the common difference is 2. To summarize the third example, the array 1, 3, underscore, 7 has a consistent difference of 2, and inserting 5 makes it a proper arithmetic progression. Now, let's review the constraints of this problem. The array length is at least 3 and can go up to 10,000 elements. The values in the array can range from -100,000 to 100,000. Importantly, there will always be exactly one missing number, ensuring the sequence can be completed as an arithmetic progression. Keep in mind a few edge cases. The missing number could appear anywhere in the sequence, at the start, middle, or end. The common difference might be positive or negative, and the solution must handle large arrays efficiently to meet the constraints. To solve the problem of finding the missing number in an arithmetic progression, let's first consider a brute force approach. The intuition here is straightforward: reconstruct the arithmetic progression and identify where the sequence breaks. We begin by calculating the common difference, denoted as d, which is derived by taking the difference between the last and first elements of the array, divided by the total number of elements, including the missing number. Once we have d, we traverse through the array, checking the difference between consecutive elements. If a deviation from d is detected, we can deduce the missing number from the gap. This method is simple and requires only a single pass through the array, making its time complexity O(n). Additionally, since no extra space is needed, the space complexity is O(1). However, the brute force approach comes with some drawbacks. Calculating the common difference d can introduce errors in languages that handle floating point operations with limited precision, potentially leading to incorrect results. Another inefficiency is that this approach doesn't fully exploit the fact that the array is sorted. Now, we can consider a more optimized solution using binary search. The idea here is to use the properties of an arithmetic progression. Specifically, at any index I, the difference between the value at that index and the first element of the array should equal I multiplied by the common difference d. If this property fails at any point, the missing number must be in the half of the array where the deviation occurred. Using this property, we can systematically narrow down our search space with a binary search algorithm to efficiently locate the missing number. The binary search approach has significant advantages. First, the time complexity is reduced to O log n, because we repeatedly have the search space. This is a significant improvement over the linear traversal required by the brute force method. Moreover, the space complexity remains O(1), as no additional memory is needed. However, there are some trade-offs. This method is slightly more complex to implement compared to the brute force approach, especially for those unfamiliar with binary search. Nevertheless, the efficiency gained, particularly for larger arrays, makes it a compelling choice. By leveraging the sorted property of the array, this method ensures that the missing number is identified with minimal computational effort. The chosen strategy is based on a key observation: the missing number in an arithmetic progression can be detected by utilizing the relationship between indices and the common difference d. The fact that the array is sorted naturally lends itself to the application of binary search, which optimizes the search process. By calculating d using only the first and last elements of the array, we ensure that the missing number can be pinpointed accurately. This approach was selected because it is significantly more efficient than the brute force method, reducing the time complexity from O(n) to O log n. It also avoids potential pitfalls with floating point precision, as comparisons are made directly between indices and values. While the binary search method requires a bit more effort to implement, its scalability and robustness make it the superior choice for this problem. In conclusion, the binary search approach stands out as the optimal solution for identifying the missing number in an arithmetic progression. Its efficiency, accuracy, and ability to leverage the sorted nature of the array make it the preferred method. By reducing the time complexity to O log n and avoiding issues with precision, it provides a robust and scalable solution. While it may be slightly more complex to implement than the brute force method, its advantages far outweigh the trade-offs, particularly for larger datasets. This makes it the recommended strategy for tackling this problem effectively. In this problem, we are tasked with finding the missing number in an arithmetic progression, or AP for short. An AP is a sequence where the difference between any two consecutive terms is constant. For example, in the sequence 2, 4, 6, 8, the difference between terms is always 2. Now, if one number is missing, our goal is to identify it. To do this systematically, the first step is to calculate the total number of terms that should be in the sequence, as well as the common difference, denoted by d. Let's start by identifying the key variables. Suppose the input is an array ARR that contains the sequence with one missing number. The length of this array will be one less than the expected length of the complete sequence. So we calculate the total number of terms, denoted as n, using the formula n equals len, ARR, plus 1. Next, we compute the common difference d. This can be determined by looking at the difference between the first few elements of the array. Specifically, we use the formula d equals min, ARR, 1, ARR, 0, ARR, 2, ARR, 1. By taking the minimum difference, we ensure that our calculation is accurate even if the missing number is near the start of the sequence. Once we have the value of d, we can move on to locating the missing number. To do this, we iterate through the array and look for any gaps in the progression. Starting at index 0, we check the difference between each pair of consecutive elements. If the difference between ARR, I plus 1, and ARR, I, is greater than d, it means we've found the gap where the missing number should be. The missing number can then be calculated as ARR, I, plus d. Once the missing number is identified, we can exit the loop. We also need to account for edge cases. For example, if the missing number is at the start of the sequence, this would manifest as a larger than expected difference between the first two elements. In such cases, the missing number is simply ARR, 0, d. Similarly, if no gap is found during the iteration, the missing number must be at the end of the sequence, and its value will be ARR-1 plus d. Finally, it's important to validate the input to ensure the array length and progression are consistent with the problem constraints before applying the algorithm. To better understand the algorithm, let's discuss some key insights. First, why do we calculate d using only the first few elements of the array? The reason is that the missing number could distort the calculated difference if we used all elements. Taking the minimum difference from the first few terms ensures we determine the true common difference of the progression. Next, why do we iterate through the array to locate the missing number? The missing number creates a gap in the sequence that is larger than the expected difference. By checking consecutive differences, we can precisely identify where this gap occurs. Finally, let's consider the efficiency of the algorithm. It operates in O(n) time complexity because we only need a single pass through the array to find the missing number. This makes the approach both simple and efficient for solving the problem. Now, let's discuss the data structures involved in this algorithm. The input array ARR is the core data structure. It holds the sequence of numbers with one missing value, and it's iterated directly during the process. Importantly, no additional data structures are required, which keeps the algorithm space efficient. Beyond the array, we use a few simple variables like d to represent the common difference and n to represent the total number of terms in the complete sequence. These variables are straightforward and essential for calculating and verifying the progression. Let's walk through an example to see the algorithm in action. Consider the input array ARR equals 2, 4, 8, 10. First, we calculate the common difference d. Using the formula d equals min, ARR 1, ARR 0, ARR 2, ARR 1, we find d equals min, 4 to 2, 8 to 4 equals 2. Next, we iterate through the array to identify the missing number. Checking the differences, we find that ARR 1, ARR 0 equals 2, which is equal to d, so there's no gap. However, ARR 2, ARR 1 equals 4, which is greater than d. This indicates a gap, and we calculate the missing number as ARR 1 plus d equals 4 plus 2 equals 6. Thus, the missing number in the progression is 6. Finally, let's analyze the complexity of the algorithm. The time complexity is O(n). Calculating the common difference d from the first few elements takes constant time, or O(1). Iterating through the array to find the missing number requires a single pass, which takes O(n) time. Combining these, the overall time complexity is linear, or O(n). Regarding space complexity, the algorithm uses no additional data structures, as it operates directly on the input array and employs only a few simple variables. Therefore, the space complexity is O(1), making the solution both time and space efficient. This solution efficiently finds the missing number in an arithmetic progression using a binary search approach. Here's how it works. 1. Input array and length. We start by determining the length of the input array ARR. This helps in calculating the common difference of the arithmetic progression. 2. Common difference calculation. The common difference d is computed by subtracting the first element from the last element in the array and dividing the result by the total number of elements in the complete progression, including the missing one. The division is integer division because all elements in the progression are integers. 3. Binary search initialization. We initialize two pointers, left and right, to represent the bounds of our search. Initially, left is 0, and right is the last index of the array. For binary search loop, inside the loop, we calculate the midpoint mid. We then compare the value at ARR mid with the expected value at that position, which is calculated as ARR 0 plus mid asterisk d. If ARR mid matches the expected value, it means the missing number must be in the right half of the array, so we move the left pointer to mid plus 1. Otherwise, the missing number is in the left half, so we move the right pointer to mid. 5. Termination. The loop ends when left equals right. At this point, the missing number is located at the position left, and its value is calculated as ARR 0 plus left asterisk d. 6. Return value. The function returns the missing number as the result. This approach is efficient with a time complexity of O log n due to the binary search, making it well suited for large input arrays. The use of integer arithmetic ensures that the solution is accurate and avoids potential floating point precision issues. This is the Java implementation for LeetCode problem number 1228, missing number in arithmetic progression. The logic mirrors the Python implementation, utilizing binary search to efficiently identify the missing number in the sequence. Key differences include explicit type declarations for variables and the use of Java's class structure. The common difference, d, is calculated from the first and last elements of the array, and the binary search algorithm narrows down the missing number's position in logarithmic time complexity O log n. To solve this problem, we start by understanding the input array and calculating the common difference, denoted as d. In the first example, the input array is 5, 7, 11, 13, with a length of 4. The common difference can be determined using the formula ARR-1, ARR-0, // which gives us 13 to 5, // 4 equals 2. Now that we have d, we proceed with a binary search to efficiently locate the missing number. We initialize two pointers, left at index 0 and right at index 3, the boundaries of the array. In the first iteration, we calculate the middle index as mid equals left plus right //2, which evaluates to 1. The expected value at this index, based on the arithmetic progression formula, is ARR 0 plus mid *d, or 5 plus 1 *2 equals 7. Since the actual value at ARR 1 matches the expected value, we conclude that the missing number lies in the right half of the array. Thus, we update left to mid plus 1, which is 2. In the second iteration, we recompute mid as left plus right /2, yielding 2, and the expected value becomes 5 plus 2 *2 equals 9. This time, the actual value at ARR 2 is 11, which does not match the expected value. This tells us the missing number must be in the left half, so we update right to mid, which is 2. At this point, both left and right point to index 2, signaling the end of the binary search. The missing number can now be calculated using the formula ARR 0 plus left *d, which evaluates to 5 plus 2 *2 equals 9. Thus, the final output for this example is 9. Now, let's consider another example with the input array 15, 20, 25, 35. The first step is to calculate the common difference d. With an array length of 4, we use the formula ARR-1 ARR0 /n to compute 35 to 15 /4 equals 5. Next, we initialize the pointers left at 0 and right at 3 to begin the binary search process. In the first iteration, we calculate the middle index as mid equals left plus right /2, which gives 1. The expected value at this index is ARR 0 plus mid *d, or 15 plus 1 *5 equals 20. Since the actual value at ARR 1 matches the expected value, we move the search to the right half by updating left to mid plus 1, which is 2. In the second iteration, mid becomes left plus right /2, which evaluates to 2. The expected value at this index is 15 plus 2 *5 equals 25, and since ARR 2 equals the expected value, we again move to the right half by setting left to mid plus 1, which is 3. In the third iteration, mid is calculated as left plus right /2, yielding 3. The expected value at this index is 15 plus 3 *5 equals 30, but the actual value at ARR 3 is 35, which does not match. This discrepancy indicates that the missing number is 15 plus 3 *5 equals 30. Therefore, the final output for this example is 30. Now, let's analyze a third example with the input array 1, 4, 7, 10, 16. The array has a length of 5, so the common difference d is calculated as ARR-1 ARR0 /n, which evaluates to 16 to 1 /5 equals 3. With this value of d, we initiate binary search by setting left to 0 and right to 4, the indices of the array's bounds. In the first iteration, the middle index is determined as mid equals left plus right /2, or 0 plus 4 /2 equals 2. The expected value at this index is ARR 0 plus mid *d, which evaluates to 1 plus 2 *3 equals 7. Since ARR 2 matches this expected value, we narrow our search to the right half by updating left to mid plus 1, which becomes 3. In the second iteration, we calculate the middle index as mid equals left plus right /2, which evaluates to 3 plus 4 /2 equals 3. The expected value at this index is ARR 0 plus mid *d, or 1 plus 3 *3 equals 10, and since ARR 3 matches this value, we again update left to mid plus 1, making it 4. Now, the binary search concludes as left points to index 4. The missing number is calculated as ARR 0 plus left *d, which evaluates to 1 plus 4 *3 equals 13. Thus, the final output for this example is 13. To analyze the time complexity of the solution, we start by breaking down each operation. First, the common difference of the arithmetic progression is calculated using the formula ARR-1 ARR0 /n, where n is the length of the array. This involves a constant number of arithmetic operations, subtraction and division, which take 1 time. Next, the binary search plays a crucial role. In this step, we repeatedly divide the search space in half. For each iteration, we calculate the middle index and compare the value at that index to the expected value using the formula ARR, 0, plus mid asterisk D. This halving of the search space continues until the left and right pointers converge. Since the search space is reduced by half with each iteration, the number of iterations is proportional to log n. Therefore, the binary search step takes O log n time. Finally, after the loop ends, the missing number is determined using another constant time calculation, ARR, 0, plus left asterisk D, which also takes O, 1, time. Combining these steps, the dominant factor in the time complexity is the binary search, making the overall time complexity O log n. When we combine all the steps analyzed earlier, the total time complexity of the solution is O log n, as the binary search operation dominates. Now, let's look at the space complexity. The solution operates directly on the input array without creating any additional data structures. The array ARR is provided as input, and no copies or modifications are made, meaning it does not use any extra space for the input. Additionally, the algorithm only uses a constant number of variables such as n, d, left, right, and mid to perform calculations and manage the binary search. Each of these variables occupies a fixed amount of memory, regardless of the size of the array. As a result, the space complexity of the solution is O1, as the memory usage remains constant regardless of the input size. To better understand the efficiency of this optimized approach, let's compare it to a brute force solution. A brute force method would involve iterating through the array and calculating the expected value for each index based on the common difference. In this case, we would perform a linear scan of the array, comparing each element to its expected value. This approach requires O(n) time because we examine each element one by one. However, like the optimized solution, the brute force method also uses a constant number of variables, meaning it has a space complexity of O(1). In contrast, the optimized solution significantly reduces the time complexity to O log n by leveraging binary search, while still maintaining the same minimal space usage. This makes the optimized approach far more efficient for larger datasets. Now, let's analyze the best, average, and worst-case scenarios for the time complexity of this algorithm. In the best case, the missing number is found early during the search, perhaps in the first or second iteration. Even in this scenario, the search space is halved logarithmically, so the best-case time complexity remains O log n. In the average case, the missing number is located somewhere in the middle of the array. Here too, the number of iterations required is proportional to log n, so the average case time complexity is O log n. Finally, in the worst case, the missing number is found at the end of the search process, meaning we perform the maximum number of iterations. However, since binary search always operates logarithmically, the worst case time complexity is still O log n. Mathematically, this behavior can be explained by the fact that each iteration reduces the search space by half. Starting with n elements, the number of iterations required is determined by solving the inequality n/2 to the power of k equals 1. Taking the logarithm base 2 gives us k equals log 2, n, confirming the logarithmic time complexity. Thus, we can conclude that the time complexity of the binary search algorithm used in this solution is O log n. To summarize, the optimized approach achieves a time complexity of O log n and a space complexity of O(1). This efficiency makes it highly suitable for cases where the input size is large, as it drastically reduces the number of comparisons needed compared to the brute force method. By minimizing both time and space overhead, this solution demonstrates how binary search can be effectively applied to problems involving arithmetic progressions. When solving this problem, there are several common mistakes to watch out for. One frequent error is incorrectly calculating the common difference d. Often, people assume d is simply the difference between the first two terms of the sequence without confirming if this difference holds true across the entire sequence. This can lead to incorrect results, especially if the missing number is near the start of the sequence. Another pitfall is neglecting edge cases where the missing number is at the very beginning or end of the progression. Algorithms that assume the missing number is always in the middle will fail in these situations. Lastly, some try to brute force the problem by using nested loops to reconstruct the sequence one term at a time. This approach unnecessarily increases the time complexity to O(n squared), which is inefficient and should be avoided, especially for larger inputs. Another mistake involves not using integer arithmetic when calculating the common difference or the expected sum of the sequence. Relying on floating point division can introduce rounding errors, particularly with large numbers, leading to inaccurate results. Additionally, skipping input validation is another common oversight. For example, assuming the input array always adheres to the constraints, like being a valid arithmetic progression with one missing number, can cause runtime errors or incorrect outputs in edge cases. Proper validation ensures that your algorithm handles unexpected or malformed inputs gracefully. From an interview perspective, this problem is often designed to test your ability to recognize patterns in sequences and apply mathematical properties efficiently. For example, identifying that the sequence is an arithmetic progression allows you to leverage formulas for sums, simplifying the solution. It also provides an opportunity to discuss the trade-offs between different approaches. While a brute force solution runs in n² time, more efficient methods like binary search achieve log n, and using the arithmetic sum formula offers n. Knowing when each approach is most suitable is key. Furthermore, interviewers may probe how you handle edge cases, such as sequences with only 2 or 3 elements, missing numbers at the start or end, or very large input sizes. Addressing these scenarios effectively demonstrates your robustness as a problem solver. This problem is closely related to others that involve missing or duplicate numbers in sequences. For instance, LeetCode 268 asks you to find the missing number in a range 0, n, which is a simpler version of this problem. LeetCode 287, on the other hand, involves finding a duplicate number, often using similar binary search techniques. This problem, LeetCode 1228, directly focuses on arithmetic progressions, while LeetCode 1539 adds complexity by asking for the kth missing positive number. When it comes to alternative approaches, brute force is straightforward but inefficient. This involves reconstructing the sequence term by term using the common difference and comparing it to the input, which has a time complexity of n². While simple to implement, it's not ideal for larger inputs. The arithmetic sum formula is a more efficient method, running in n time. Here, you compute the expected sum of the sequence and subtract the actual sum to find the missing term. However, this approach requires careful handling of integer arithmetic to avoid rounding errors. Binary search is another powerful technique for solving this problem. By leveraging the sorted nature of the input, you can efficiently locate the point where the sequence deviates from the expected common difference d. This approach has a time complexity of log n, making it optimal for larger datasets. However, it may be less intuitive compared to using the arithmetic sum formula, as it requires a solid understanding of how to apply binary search in the context of arithmetic progressions. Each of these methods has its own trade-offs, and understanding when to use binary search versus other approaches can be a valuable discussion point in an interview setting. Great job following along. To summarize, we tackled the problem by exploring a brute force approach, emphasizing the importance of understanding arithmetic progression properties. Remember, brute force is a useful starting point, but always aim for optimization when needed. Thanks for your time, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!